And the textbook questions in this section are okay, but I had some that I liked even better. So what we're going to do is look at a bunch of real-life examples where sinusoidal graphs appear. Okay, one of them is with tides. So tides coming in and tides coming out. Now this is going to be the easiest application question that you can get because they give you the equation. So we've got that the depth is negative 4.5 cos 0.16 pi t plus 13.7, and we want to sketch the graph. So I'm going to erase this. And off to the side, we're going to think about doing the DABC. Our equation has a d value of 13.7 and an amplitude of 4.5. So when I'm going to draw this one, it makes sense that I would have my axes like this. And I'm going to pick a random place to put 13.7. And as soon as I do that, I set a scale that this length is 13.7. But I can label my sinusoidal axis at y equals 13.7, and I've completed the d-value. Next, A, your amplitude. Your amplitude is 4.5, and so we need to go up 4.5. That'll get us to about, and then try to estimate how much 4.5 would be. Up 4.5 takes me to 18.2. Down 4.5 takes me to 9.2. That's our max and a minimum. Our A value, our amplitude is now done. Next, we need to use our B value to calculate our period. So when we go to our formula is our period is 2 pi divided by the B value, which is 0.16 pi. Okay, this would be a calculator question. Pi's cancel out. 12.5. So we mark one full period. And in real life examples, it makes sense that we have numbers along the bottom rather than things in terms of pi. Split that in half, 6.25. Split that in half, 3.125. Count by 3, and we would get 9.375. So we've marked one period, and our B value is done. Next, we temporarily draw our graph without the shift. But can you see in this one there is no shift? So the temporary part can be done because whatever the temporary one, your actual graph is going to be that in the end. It's a negative cos graph. Where does a negative cos graph start? At a minimum. So go minimum, center line, maximum, center line, minimum. So there's part A. Part A was just sketching our graph. And hopefully that activity that we did on Friday, you guys are all feeling really confident about your graphing sinusoidal skills right now. Part B, okay. Part B says a bulk carrier needs at least 14.5 meters of water to dock safely. How many hours per cycle can the bulk carrier dock safely? So if we go to our graph and we go and we label 14.5 on here, that would be about here. If I draw a line across at 14.5, does it make sense that it needs more water than 14.5 to dock safely? So the only part of our graph that makes sense is this section here. So we're going to solve this first by using our graphing calculators. And then we're going to look at how we would solve it algebraically. So for your IB course next year, this is something you would do a lot of. You would use your graphing calculator. The first thing you want to do is be able to type the equation in there and set up your screen so you see this green curve just like we see it on, just like we drew it. So we want to set up our graph so this whole thing appears exactly the same. So we go to our graphing calculator, turn it on. So we had negative 4.5, and make sure you use the negative sign, not the subtract sign. Cos 0.16 pi t, so we have to use an x, plus 13.7. Okay. First of all cos graphs with a period are always in radians, so we need to make sure that we go to our mode and make sure that our graph is in radians. Now, if you just hit graph right now, whoo, that's all you're probably going to see, unless your window is set up even differently. So what we need to do, in order to see this window, we need to set both our x-axis and our y-axis to match what we have here. So my maximum one period is at 12.5, so maybe I'll want to go a little bit further than 12.5. And my maximum y value is 18.2, so maybe I want to go a little bit higher than 18.2. So the way that you do that is you hit your window button on your calculator. Okay? We don't need to go far into our x-min, so maybe you just start at -2 or -1, just so that you can see your y-axis. Then we went up to 12.5, so I'll go a little bit further than that. 15 should be fine. Do you know what the XSCL stands for? It's the X scale. So it's going to, right now it would put a ticky mark at every 1. If I want the ticky marks exactly where I had them, they were going every 3.125. You can do that, and then you'd have just those 4 that we saw. Y-min, we don't need to go into the negatives too far, -2. Let's go up to 20. And our scale there, you can't make it hit that center line perfectly. Maybe we just want to go by 5s. Now when I hit graph, it matches up and looks very similar to the graph that we drew. Next, we can go back to y equals, and in y2, we can write the 14.5. That would be a horizontal line at y equals 14.5. And when we graph that, that represents that the water needs to be deeper than that in order for it to dock safely. Now, how do we find out where these two graphs intersect? There's a lot of stuff under the calculate button, so you need to push second and then calculate. And number 5 is intersect. So if you go number 5, enter, and you go enter once for the first curve, enter once for the second curve, enter once for the third curve, and then it asks you to guess, not the third curve, but it asks you to guess, push enter again, and it will tell you that one of them is at 9.02. So we can label that first one at 9.02. In order to find the other one, you go to the intersect again. It will always find the intersection that's closest to the cursor. So right now, I'm going to move my cursor that does look closer, but that would make me nervous because if it all decided to go to the other one, I have to do this all again. So I'll go a little bit more. Push enter on the first curve, enter on the second curve, enter when it guesses, and it finds the other one at 3.48. So if we did 9.02 minus 3.48, okay, I'll come check it. So it can be safe for 5.54 hours, or about 5.5 hours. Oh, so go back to your y equals. See how your plot is labeled? Go up to that plot. Highlight it. Yeah, and push enter to turn it off. And now go back to y equals. There you go. Now it should work. So you'll find that next year in your IB course, they'll ask you questions like this, and using your graphing calculator, what we just did, is much faster than it would be to calculate it. Okay, I'm going to show you how you would calculate it, and you're not going to have enough time to write it down, but it'll be on the video if you do want to look at it later. Okay? In university, you'd be asked to calculate it by hand. But the amount of time that it takes, and you need a calculator, then the IB course says, well, if you need a calculator anyways, why don't you use the calculator in its faster method than in its slower method? So here's how we would go about solving it without our calculator. Okay, we want to find out where it intersects when the depth is 14.5. So you know the y value is 14.5, and you could plug that into your equation. The only thing you don't know now is t. Anytime there's only one variable in an equation, you can solve for it. So the way that we're going to solve for it is we are going to get cos by itself. So I move the 13.7 over. Again, you probably won't have time to write this, so just watch. And then divide by negative 4.5 to get cos by itself. Now, the way that this looks right now is complicated because there's a whole bunch of stuff inside. So what we do sometimes in math is we say, let's just make it simpler for a bit. So I'm going to let theta equal everything inside. So then I can change my question to just this equals cos theta. That's something you've solved before. Obviously, it's not on your pie plate. So you would need to find your reference angle. How do you find a reference angle? You do cos inverse of the positive value, not the negative value. And we find out our reference angle is 1.39. If cos is negative, it's in quadrants 2 and quadrants 3. So once you have your reference angle, you could find your answer in quadrant 2, and you could find your answer in quadrant 3. Makes sense so far? So the only thing that's kind of new in this one is this little substitution that I did. Just because it looked complicated, it made it look simpler. Now I've got an answer for theta, 17.495 and 4.533. But I wanted to solve for t. So now we substitute back. We substitute back instead of theta equals all of this. You could divide by the 0.16 pi, and you find out the first answer is 3.48. The same as what we got on our graphing calculator. Do the same thing for the answer in quadrant 3, and you'll get 9.02. So we can say that the ship is safe for 5.54 hours. So the tricky part in this one, if you were doing it by hand, which you would probably be expected to do once you get to university, is that little substitution keeps it simple, gets your reference angle, solves it. It would be kind of, some people don't switch it back, but then you would get a 0.16 pi t reference angle equals, and it's just a little bit awkward. All right, let's go to our second question. A Ferris wheel has a radius of 15 meters. It rotates once every 20 seconds. Passengers start at the bottom of the Ferris wheel. That seems to make sense. It's very hard to get on the top, which is 1 meter above the ground. So we want to graph this and find its equation. So in this situation, sometimes it makes sense to first draw a picture. Here's our Ferris wheel with beautiful chairs. There we go. There's a happy person on the Ferris wheel going for a ride. Okay? Then off to the side, just take this, move it down a little bit. Off to the side here, we can draw what's happening, okay, based on the information they've given us. So all we know is the radius of the Ferris wheel is 15 meters. So that means from here to here is 15 meters. It rotates every 20 seconds. So if we get on at 1 meter, does it make sense that 20 seconds later, you're going to be back at 1 meter? Where are you going to be at 10 seconds? The very top. So where is, according to my picture, the very top is right here. What number will I put for the very top? 31. How did you come up with 31? Right, because our radius is 15, right? So our diameter would be 30. And so our amplitude's going to be 15. That means I know my center line's right at 16. And when are you going to be on the center line? At what times? At 5 and 15. And this could continue on. I guess technically I should not. You start there, so you're not going back in time. And your Ferris wheel goes around and around and around. So now based on our picture, do we have everything that we need to work backwards to get our equation? Yes. Do we know our d value? Well, that's our center line. That's at 16. Do we know our amplitude? Yes. Our amplitude is 15. Our b value is calculated from our period. We have a formula that's period is 2 pi over b, and that formula rearranged says that our b value is 2 pi over our period. Since it takes 20 seconds to rotate, we can now say that our b value is 2 pi over 20. And even though that reduces to pi over 10, I actually prefer 2 pi over 20. Because when it's written 2 pi over 20, I can see the period is 20 right away. If it's written as pi over 10, you'd have to do some manipulation to figure it out. And then I'm going to leave the c value because there's actually more than one equation for this. So, first of all, we could choose a sine graph. If I choose a sine graph, then my amplitude is 15, sine, my b value is 2 pi over 20, factored out, x, and then my d value is 16. And where does a sine graph start? Center line going up. When does that happen? A shift of 5 to the right. The center line going up is shifted 5 to the right. So this would be a minus 5. Can you see that you could also make a cos graph? Amplitude wouldn't change. Period wouldn't change. Center line doesn't change. But where does a cos graph start? At a maximum. So you can have x minus 10. Because it's shifted, the maximum is 10 to the right. And then you're like, oh, but if a negative cos graph starts at the minimum, then I don't need a shift. So this is another possibility. Make a negative cos graph. Can you see you could make a negative sine graph if you shifted 15 to the right? And since it continues, there's more answers that are possible. We could spend all day coming up with new equations if we wanted to, because they would just happen over and over and over again. Okay? For part B here, it says estimate the height after 22 seconds. So it says estimate, so this is just mental math. If we went on here, 22 would be right here. Does it make sense that at 25, it'd be back at the center line? So we need to estimate it somewhere between 1 meter and 6 meters. If it swooped up there again. So we could go there and go, maybe I estimated at, what do you think? 7 meters? Perfect. And since it's an estimate, that would be fine. Oh, some things about our graph that we did not do. Okay? I labeled time, which was good, but I didn't label on this side. I should label that this is height and put the units in meters. It was meters, right? Not kilometers. That'd be quite the Ferris wheel. 20 seconds. Wow. And then we should give, in fact, in the IB, they want you to label your x-axis and your y-axis as well. Lots of labeling. So that is a better sketch of the graph. If you wanted to find out exactly what happens at 22 seconds, we'd have to go to our graphing calculator. Type one of those equations in. So I'm going to do the negative cos graph because then I don't have to put in a shift. Negative cos. 2 pi over 20. Oops. X bracket plus 16. And go to my window, and since now my Ferris wheel is going, I'll go up to 25. We're going by 5s. We need to go up by 35s and hit graph. Should see the whole Ferris wheel. Now to calculate a specific value, again, you go to second calculate. Number 1 is value, and you can just push 22 in. And it was only at 4 meters, so our estimate was off a little bit. But based on our graph, it was fine. And then the second part says, estimate at what time you will be 20 meters above the ground. So if we go back to our graph here, try to decide where 20 would be. There or there. 2 possible answers. How would we find that with our graphing calculator? So an estimate, can you say maybe at 6 seconds? So that would be our estimate. To find out our actual value, we would go to y equals, put in 20 for our second equation, and here calculate where they intersect. enter, enter, enter. So 14.14. Question. I figured out the 14.14 with my calculator. Can you tell me a way I could calculate this one without? The difference between 10 and 15 is 5.
No, sorry, 10 and 14.4.
So you're going up 4.14? So you would go, is that what you mean?
You
Subtract 4.14?
Yeah.
And you get 5.86. Because it's symmetrical. Okay, we're going to do one more example together. World's highest tides are at the Bay of Fundy. They're periodic in nature. At a dock in the bay, a maximum depth of water of 8 meters is measured at 4:30 a.m. 6 hours and 12 minutes later, it's at 10:42 a.m. So again, this is the minimum amount of information that's needed to create your equation. You know at 4:30, okay, are you okay if I write 4:30 as a decimal? How would I write 4:30 as a decimal? 4.30? 4.5, because it's exactly half an hour. And if I pick 8 meters to be there, we have a maximum. 6 hours and 12 minutes later, so at 10:42. So if this is 4.5 hours, 6 would be a little bit more. What decimal place am I going to write for 10:42? Close. How do you figure that out? It's more than half, right? Because if 4:30 is 0.5, 42 minutes will be more than half. It's good. Looking at 60, what happens if you do 42 out of 60? Could you divide them both by 6? Get 7 out of 10. So this will be at 10.7. And that's our minimum at 2 meters. So this is depth in meters. This is time in hours. Our title for this will be tides. This is our y-axis. This is our x-axis. And at 2 meters.
So we assume that this is just one period?
Well, this won't be one period because you're going from maximum to a minimum.
Well, I mean, like...
But it is the next time it has a minimum, and it's periodic in nature. So that means another 6 hours and 12 minutes later. Can you see you went up by 6.2? I could mark that same distance here, add 6.2 again to get to 16.9, and I'll be back at my maximum. My center line is going to be right in between these. It's going to be y equals what number? Y equals 5. So you're looking for that value that's right between 8 and 2. Couple ways you could do that. You could just mental math and guess and check and pick a number and see, yeah, it's 3 away and 3 away. Right? You could add 8 and 2 and divide by 2 to find the average. 8 plus 2 is 10, divided by 2 is 5. And then if this is one period, we normally separate our period into 4 equal sections. So we could add a section here and a section here. And then if from 4.5 to 10.7 is 6.2 hours, I would have to go up 3.1. So that'll get me to 7.6 and go up 3.1 to get me to 13.8, and that's when it will be on our center line. So with this, we have enough to work backwards to find all of our equations. Our first let's write out the d, the a, and the b, because we can figure those out. Our d value is 5. Our amplitude from the center line to the maximum is 3. We can find our b value by doing 2 pi over the period. What is the period of this function? From there to there. .4 hours. So it's not just from the maximum to the minimum, because that's not one full cycle. You have to go from a maximum to another maximum. 12.4 hours, so our b value is going to be 2 pi divided by 12.4. And our c value we leave because it could change whether we use a sine graph or a cos graph. But now we can start by saying, I can write a sine graph, 5. Oh, amplitude is 3. Y equals 3 sine 2 pi over 12.4 x, leave a space, and my d value is 5. And same thing for cos. Everything will be the same. Except for the start. Where does the sine graph start? At the center line going up. Can you see that you would have that at 13.8? Can you see if you subtracted 3.1? You could have also used 1.4, and it doesn't matter which one you use. Both would be fine. Then, for our cos graph, starting at a maximum, we have a maximum of 4.5 to the right, so we could have minus 4.5. Then part B says estimate the water at 1:30 p.m. Where is 1:30 p.m. on your graph? Sorry? How would be 1:30 a.m.? 1.5. Where would 1:30 p.m. be? 13.5. So it's going to be pretty close to 5. So and again, it just said estimate. So we'll do an estimate of 4 meters. If you wanted to find it out exactly, you need to go to your graphing calculator and plug it in. So there's 2 more graphs on there for you to try on your own.